This one? Okay, so hello everyone. Thank you for being here. So I am going to present today an experimental study about low-rank semi-definite programming for symmetric tensor decomposition. So I am going to start with an introduction, then I will present the project context, the SDP formulation, then I'm going to show some numerical results, and I will end by a conclusion. So there are many real-world applications that involve the incomplete data with underlying low-rank and positive semi-definite structure, such as polynomial optimization and, for example, machine learning. Semi-definite programming plays a central role in global and polynomial optimization. However, its use for the tensor decomposition via matrix completion for moment matrices remains underexplored. So in this talk, I'm going to present an SDP-based approach for recovering the full moment matrices from incomplete data. So I'm going to use standard SDP solvers, such as CSDP, Clarabelle, Mosaic, Cosmo, Hypatia, and some of the low-rank oriented interior point methods, such as Lorraine and IPLR-BB. Let's start from the problem formulation. So if you have a homogeneous polynomial f with a degree d and with n variables, we want to find a minimal rank or minimal decomposition of f of the form of the sum of powers. So here we have, for example, we want to find the expression for f or decomposition for f up to r components, and our unknowns are omega i's and xi's. So the minimal r here in this decomposition is called the rank of f. So as I said before, we want to find the omega I and xi, and if you are going to work with f, it will be too difficult because this problem will be nonlinear and non-convex and hard to compute. So we can use the upper product, and we can associate to f a linear functional f star on the ring k of x, where x is multi-index up to n. So by using the weighted sum of evaluations theorem, so we can represent f stars as a sum of as a linear sum of the omega i's and delta xi's, where delta xi's are the xi's, which are the Dirac measure of at xi's, or xi's are just the evaluations of the polynomial at xi. So we can define a compact set S in Rn, and we can define the positive measure sets supported on S. And when we have omega i's positive, that are positive, and xi's are in S, then f star is represented by the measure, which is the sum up to r, which is the sum of omega I delta xi's. Delta xi is, as I said before, is the Dirac measure at xi. Its moment is up to degree d are unknown and given by this formulation, which is the f alpha here is the coefficient of the initial polynomial, and this one is the inverse of the multinomial coefficient. And the moment matrix in degree d prime, which is bigger than d, is given by this by the measures. So, and the moment matrix is also of rank R and is PSD matrix, which is positive semi-definite matrix. So the moment matrix H has a multivariate Hankel structure indexed by multi-indices alpha and beta in Nn. And with and they are lower than degree d prime, which is bigger than initial degree d. So as an example, if we took n for two variables and d prime as our degree, so we can have this representation of this Hankel structure matrices, and we can see that there are some coefficients that are repeated, which, for example, this one, mu11 and mu11 here. And this is coming from the monomials, the product of the monomials that are still in the same basis of basis B. So as I said before, our objective is to recover the full moment matrix H of degree d prime bigger than d by solving an SDP problem with constraints. So let's formulate this problem by as a standard SDP problem by minimizing the trace of H. H here is our Hankel matrix to recover, and it is subject to some linear constraints. So H here is symmetric moment matrix to recover, as I said, and it has a low rank solution. And the matrices AIs are defined as follows. If the product of the monomials in L, AAG will take 1, otherwise it is 0. And L here is the set of monomials up to degree D. The same thing for the right-hand side of the linear constraint, which is BK. It is given by the product of the coefficient of the polynomial multiplied by the inverse of the multi-binomial coefficients, and it is equal to this entity if Fk is in the set of the coefficients of F. Otherwise, it will be 0. We can use also a nonlinear formulation given by the Borer-Montero formulation. The idea here is representing the matrix variable H in low rank format, which is equal to U times U transpose. And here U is N times R matrix, and R corresponds to the rank of the matrix H. So we can use this formulation for nonlinear solvers. So we evaluated this SDP formulation using the solvers that I presented before. And I selected only 3 representative runs that showing the iteration counts, the memory usage, and the execution time. And I used different problem size. We can see that only Clarabelle, CSDP, Mosaic, Hypatia, and Nitro that managed to solve all the problem instances. However, there are some, the other solvers failed to solve all the problems, especially when we are increasing the size. So let's make a look for the different characteristics and the results of the different solvers. So for Mosaic, it slows down as the problem size increases, but the performance improves when enable the parallelism. And Mosaics use the pre-solves, some parallel computing, Cholesky factorization technique to reduce the memory usage and accelerate the solve. For CSDP, it has very low memory usage across all sides of the problem, and moderate runtime that increased with when we are increasing the problem size. And this is because that CSDP exploits the sparse matrix structure and employs hidden diagonal block detection along with advanced optimization technique in the implementation. For Clarabelle, it is a robust solver. However, the memory and the time were increasing drastically, especially for larger problems. And this is due to the fact that they are not exploiting the block and the sparsity structure within the PSD cone constraint, which leads to costly dense matrix operation. Hypatia is faster than CSDP and Mosaic, but with high memory usage. And this is due to the fact that it does not have automatic block detection. And so for the user should specify the structure manually for efficiency. Nitro has the best performance in terms of memory and time for larger scale problems. This one is a nonlinear solver. So it used the nonlinear formulation from Burel-Monteiro, where representing X or H in our case in low rank format. But it requires multiple restarts from different initial points since the problem is becoming non-convex. And it obviously benefits from low rank structure to reduce the memory usage. For the solvers that have partial success, I'm going to start with Cosmo, which is an ADMM-based solver. It has a lower cost per iteration than interior point methods. However, it has more number of iterations compared to the other solvers. It has a heavy memory usage caused by the eigen decomposition during the semi-definite comp projection. And the chordal decomposition can increase the memory due to duplicated variable and coupling from overlapping links. For low-rank, which is low-rank interior point method, it fails for larger scales. The low-rank preconditioner here was not used because there are some difficulties in preserving the PSD structure. IPLR-BB, which is using the interior point method, but by changing the matrix variable and enforce it to make it in this form as low rank part and mu times identity, and mu here is the barrier parameter. So this solver has a technique to find the correct rank if you start even with even with a small rank or bigger one. So when it solves the problem, it can find the correct rank, but it fails for larger scale problems because it lacks for structure exploitation and high performance matrix routines. To conclude, we can say that our SDP approach for tensor decomposition is effective. Solvers that having block diagonal structure, exploitation and sparsity and resolve technique manage to perform well on these kind of problems. However, the low rank oriented solvers often fail when we are increasing the size of the problem. So the current low rank solvers are promising in theory, but they lack robustness. And thank you for your attention. These are some references that I used in my work, and thank you.
Questions?
So, thank you for the talk. So maybe I just ask for clarification.
Yeah.
So what is the problem exactly that you solve? You have a matrix, a Hankel matrix. You know some entries, and you want to complete it to a larger degree?
Exactly. Yeah.
Or do you want to find the atoms?
For now, for up to this part, I'm going to complete this matrix. I mean to use the SDP formulation to complete all these coefficients of this matrix. And the next part will be, it wasn't mentioned here, but the next part is, since we know that the problem have a low rank solution, we want to see how to find, to exploit this low rank structure in the computation part.
So to find the atoms, you mean?
Yeah, that's the
next step.
Next goal, yeah.
Okay. And what is the data which is given? You know the moments up to degree d, and you want to extend to d prime.
Exactly. For example, for this example here, when we are working with two variables and d equal 2, so I can say that we know only these coefficients that are in the first row and the first column, of course, because it is a PSD. And we know that there are some coefficients that are the same, like this one. These are our constraints, and then we use the SDP solver to complete all the coefficients.
Okay. And your constraints, you say that you impose a moment condition.
Exactly. So for the constraints, yes.
Okay.
I'm imposing these linear constraints, and I'm creating the data matrices based on the, let's say, the position of the moments in the matrix H. For example, here using this formulation, I can formulate this constraint, for example, to make the algorithm know that this coefficient is equal to this one.
Okay. Okay, this is what you are. Yeah. And maybe you can say a word about the motivation for the objective. Why do you minimize?
Okay, so I'm minimizing the trace to promote the low-rank solutions. Because one of the outputs for this kind of problems will show this full matrix that is filled with all the coefficients. But if we check the singular values, we'll see that there are like some singular values that are big, and the other parts are too small. So we can know the rank from this formulation. But as I said, the goal is to see how to use this during the computational part and the implementation part of the algorithm.
Go ahead. Yeah. Oh, okay. I'm on.
So some of the solvers you tried were nonlinear solvers.
Yes.
Like we're directly working with factorization U transposed U. With a rectangular U, probably, right?
This one?
Yeah, probably U is rectangular. And so in this case, you can just prescribe the rank of a solution, right?
Yes.
So in this case, there is no problem, there is no concern about the rank. But if you use a semidefinite solver, a classical semidefinite solver, you don't have a rank constraint, of course. And I mean, the solutions you got, for example, with Mosaic,
yes,
were they low rank or were they not low rank?
Without low rank. All the other solvers, I use this formulation, the full rank formulation. But only for Nitro, because it is a nonlinear solver, I use this formulation.
Yes.
So this one I made it only for Nitro, because it is nonlinear solver.
Okay, so for the others, you did not care about the rank.
Yeah, exactly. Yeah.
But when this later will not lead to an algorithm for tensor decomposition, right?
Sorry?
The final goal would be to find an algorithm for tensor decomposition, and this cannot be achieved if you don't have low rank. Right?
Yes, this is as I said, the future goal, because there are some solvers that are detecting the correct rank. For example, I'm going here. Yeah, this one. You see this one, this solver is an interior point method solver, and it enforces the variable matrix to be in this format. And you can start with small ranks, even if you don't know the correct rank. And if it managed to solve the problem, it will find the correct rank.
Yeah.
So these are some techniques that are used in some solvers. But for the general SDP solvers, they don't have a technique for detecting the correct rank.
Yeah.
So it solves all the full matrix problem.
Thank you.
Can I? So I probably missed when you explained why, but so in your program, you have that the H needs to be positive. Is it really in connection with the tensor rank? I mean, if you have a tensor decomposition, it doesn't always mean that H is positive, does it?
This one is for the PSD constraint that is coming from the fact that the Hankel matrix is PSD.
Sorry? Oh, I see.
Yeah, this one. I'm imposing this constraint because I know that the moment matrix is a PSD matrix.
Okay.
So I need to compose
sorry,
as
I
a
really missed it.
yeah.
We have a question online. Didier is online. Is he?
We cannot hear you, Didier. Can you hear us? Can you try to speak again?
Can you hear me now? No? Yes, we can hear you.
Yes,
Yes.
you can now, yeah?
Yes.
Okay.
I need to unmute
So
over
I
there.
have a question on the slide, which is shown now. The role played by this set capital S, you did not mention that.
Sorry?
What's the role of capital S?
It is a compact set for that contains the CIs, which are the the distinct spans, the span distinct lines coming from the formulation of the sum of powers of the polynomial.
I did not see the localization matrix corresponding to the set capital X in your program. I just saw the moment matrix, right? But how do you encode the fact that the atoms should come from capital S?
Yeah, I didn't do this. Yeah, so I was just working on this moment matrix, but using the SDP solver for just completing the coefficients without imposing the set S or the CIs to detect it.
In the numerics, if S is a sphere or some compact set, this will be very important.
Sorry?
I think that the set capital S plays a very important role. So you should try with a set with a compact S.
Okay.
You have to
I didn't understand exactly the question.
The question of Didier is, here you say XCI are in S,
Yes.
but in your SDP formulation, this doesn't appear.
Yeah, because I'm not.
You could,
Yeah.
maybe in the next step.
Yeah, this could be as a next step if we are going to use the Vander mode decomposition, right?
The localization of the moment, the localization matrices, which can be also.
Okay. I didn't focus on this part, so I was only focused on the SDP formulation and the SDP solvers for solving low rank problems. And one of the interesting applications that Bernard suggested already is working on the moments problem.
Another question?
Yes. Well, I'm not sure. I don't know if you're familiar with the algorithm of symmetric tensor decomposition that Bernard, Comon, Brachat, and Sigaridas.
Okay.
But it's just to know if I'm understanding correct. Are you like sort of brute forcing the solving of the parameters by just minimizing the trace until a certain degree with like pure linear semi-definite programming, or?
case is a special case where it's a positive weight.
Yes, and then you solve the parameters by just.
Replace this by a convex optimization.
Okay.
But you are not sure to find the minimum.
Yeah, and
It's something which, as you said, it's the trace. Here is the sum of these singular values. It's not the rank.
yes.
It can fail.
But is it more or less complex in general than like solving the commutation of the matrices? Because you also don't need to choose the basis, so it seems like. Okay.
Thank you.
Other questions? Yes. Wow. Two.
No, yes.
It's just a clarification because I didn't quite understand. I thought you were using the Bourret-Monteiro for age. Can you afford to, because at the same time you said you're going to factorize, if you factorize age, you see that it is low rank.
Yes. Okay, for this kind of applications, we know the correct rank of the problem from the beginning.
But how do you know the correct rank?
Because my initial inputs are polynomials, and
Right, yes.
and then based on these polynomials, I'm going to formulate this problem.
Right.
And if in case I'm using
Sorry, yes.
The compact format, this one, or in the polynomials as an input, so I know the correct rank.
Right, yes.
So,
yes.
yeah.
Okay, sorry, that was my, yes. Thanks.
You may also want to look up maybe some of the papers by Didier and the MIT team around Pablo Parillo and such who have worked on the exactness. So sort of in some cases what you're doing may be exact, except sort of you're not showing it. So sort of the question of whether you know whether the sort of our rank will be precisely what you would like, that has been studied by people, and you can look up the conditions. And maybe there would be some magic simplification in those cases.
Yeah, for sure. But and up to this stage, we didn't focus actually on the rank. Just we wanted to see if the formulation is correct or not by using the SDP. Didn't manage to solve the problem correctly. And we know that we will have the rank problem, how to find the correct rank, how to use the low rank approximation in the algorithm, and it will be the next stage for this work.
Thank you.